Assalamu alaikum. In this video, I'll show you how to use the fit simulation to study the conservation of mechanical energy. The law of conservation of mechanical energy states the total mechanical energy at any position during the object's motion must be constant in the absence of a non-conservative forces like friction or air resistance. So our simulation today will let an object to slide down an inclined plane, and then as the one shown here, and then we'll calculate the total mechanical energy at A, B and C. As you know, once the object lands here, if this is the zero level, so zero potential energy level, so at point C the object has only kinetic energy, so EC equal KC. At point A, if we release the object from zero initial velocity, the energy is potential energy only, so EA equal UA. At point B here, at this interval here, we'll keep the object to move horizontally. It has only horizontal velocity, so VB equal VBX. There is no VBY. VBY at this point equal 0. Okay, then the object, it has both kinetic energy KB and potential energy UB. Okay, one more thing we have to keep it in our mind, since the object here will leave horizontally, the horizontal component of the velocity at B, VBX, same as VCX. Okay, V naught B along the y direction 0, so we can use the equation of motion to determine the time needed. We can measure the x here, the horizontal distance, and then we can find VCX value, which is VB. Then you know the kinetic energy at B, and to determine VCX we have to use the equation of motion again, VB and VC along the y direction, VCY equal VBY plus GT, and T we can find it from VB equal half GT squared, and then we can find the y h equal half gt squared from the equation of motion, and then we can determine T, which is root 2 h over g. We'll use it with x to find vc y, and then we can easily calculate the kinetic energy at the point C, and this is the total mechanical energy at C. So now I'll follow the link, I'll open it, and then I'll show you how to control some patterns in the window, and then to show you how to collect the data. Okay, for different height, for different y, we'll measure the velocity at C and the velocity at B, and then we'll calculate the energy, mechanical energy, total mechanical energy at these three positions. Okay, so now to open the simulation, click on Control, right click, and then the simulation will open. So now I'll click on this arrow till it downloaded here. Okay, and then I click on keep. If you face same thing, I'll click on this one and then open. When done, it will open when the loading is done. Okay, now this is your skate. I can make it big, I can change the shape of the track. I'll make it same as the one I showed you there. I'll make it this way, see? Okay, I can show the grades here to show the height, so now I raise this one a little up, I can make this one a little bit smaller. Okay, I raise this one a little bit up to make the initial height equal 8, and I'll make this one horizontal. See, I can move it more to the side. See, just click on the blue circle and then you can control it as you wish. Okay, this is must be horizontal this way. Okay, I'll decrease this one a little bit to make it exactly 8. Okay, so this is the 0 meter, this is the ground level, this is the zero potential energy level, and this is the height, this is point A, this is point B, and where the skater land, this is point C. I'll make the simulation speed low, okay, make it slow, and then click on choose skater to choose the skater and to see its mass. You need the mass to calculate the kinetic energy and the potential energy. So if you choose this one, it's mass 75. If you choose this skater, it's mass 60. This dog 20. This bug point 2. Okay, so I'll choose this one or this one. Okay, record the mass of this one to be 5 kilogram in your lab report. Okay, this is my skater. Again, to measure some quantities like the distance x, I'll use the measuring tape. Click on it. This is here. Okay, this is measuring tape. I'll fix it here. And now when you put this one here, it means the distance equal 0. See, the distance, I have to put it at distance equal 0, directly below the horizontal point. This is 0. Okay, I'll keep it at this point. And what more things I have to choose? As you see here, track friction, there is no friction at 0. Okay, keep it at 0. Non-conservative forces is negligible. What do you need more? That's it. Okay, so now to fill this table, this is same as the one I did. To fill this table, now start from y. You can, these ones, calculate them directly. Ka 0, because you will leave the object from point A at 0 velocity. Fill this one directly. Okay, now to fill this table, you have to measure x, you have to calculate t, where t equal t, you can find it from here. You can find VCY 2GH half to the power half radical, and then use VCY to find what, guys? To find t, where t equal VCY over G. Okay, so t here, VCY over G, and VCY equal to GH radical. Okay, now you have t, just measure x, and the other things you can calculate them. You can calculate them using the equation of motion. I'll go back to this one. Now y equal 8. This is the first one. This is the first reading in this table. Y equal 8. Just I'll measure x. Okay. So I release my object from height 8 first. Okay. Release the object. This is release it. Now it's velocity 0. I release it. Okay. And oh no, this is wrong. Okay, so I'll take it, I'll put it here. Okay, and then I release it. It will slide down the track, and it will land where? Here. This is the landing point. Okay, I can return the object, and then click on pause when it lands. Okay, to measure x. No, oh, I couldn't find it. Okay, one more. Release the object, start your measurements. Okay, and then pause it when the object almost will land. Okay, just to measure x accurately. Okay, it lands here. Right, so now I can measure x. Just to drag the meter, drag the plus sign till the point of landing here. Okay, what's the distance? 7.72. record it here. Okay, now you will change the height. You will make it 7. Okay, or keep this one as is, but leave the object from here. Okay, return, where is the object? This one I return it back to 0. Okay, so 0. Now this is your skater or your object. This is height 7. Leave it from here to move. Click on this one and then pause it when it's land. Okay, So almost here, almost here. It lands almost here. Okay, so drag the meter, measure X again. Okay, okay. Once you finish, now meter back and then put the object at height 6, release it, pause it when the ball lands almost here. Almost here. Read it. Okay, return it back to 5 meter again. See, this is 5 meter. Release it. Okay, release it from 5 meter and then pause it when it is almost landed. Okay, it's almost here. Okay, measure, 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 measure. Sorry, I have to keep this one first. I have to get back to the 0 point and then I'll measure. Okay, drag it, it's almost here. Okay, do the all steps, do the all steps here at 8, 7, at 6, at 5 and 4, and then record X, and then T, it has VCY T, VCY over G. VCY, it has constant value. VCY, it has constant value to GH over 2 radical. And then T, it has constant value. Once you have VCX, which is X over T, then you can easily find VCX squared and then VCY squared and then get VC squared and then just multiply VC squared by half M. This is the total mechanical energy at point C. KC same as EC. Now for point B, VB is VCX. Okay, and VCX is X over T, the one you determine it up. Then find VB squared. Once you determine VB squared, so KB is half M VB squared. UB is MGH. H, you have it, H in the simulation here, H is 3. See, this is the 0 energy level, 1, 2, 3 meter. Okay, so do your calculations, and then fill this, fill these 3 tables, and then at y equal 8, 7, 6, 5, 4, 3, 2, write EA, write EB, write EC. You will find that the total mechanical energy at this point, point A, same as the total mechanical energy at point B. This is point B, same as the total mechanical energy at point C for different Y. So it means what? It means the total mechanical energy is conserved in the absence of what? In the absence of what we call it, the non-conservative forces. Okay, see you in the next video.